Okay, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Good evening, everyone. For those who don't know me, I'm Faisal Alkhwaiter. I'm really happy to be standing here in front of you and giving my first PAL session this year to first year students. I'm a third year medical student. And inshallah, it's going to be about an interesting topic, which is gluconeogenesis. So, what we'll be dissecting today, inshallah, is just a very basic topic. We're going to start with knowing what sources of glucose we have. What is gluconeogenesis? I know it's a very long word. But inshallah, we'll have a very good understanding of it. How do we regulate gluconeogenesis? And these two cycles that we'll tackle, inshallah, at the end. And inshallah, this is going to be a very interactive session. So there will be multiple checkpoints and questions in the end. Okay, let's start. So basically, we use glucose as the main energy point of our body. And we can get it from multiple sources. The main one is through food. So let's say it's around 7 p.m. now. I just finished the spa session. I'm craving dinner. I just had a shawarma. Let's say I just ate that. This source of energy, after of course digesting it, would last me around 4 hours till all the glucose from that exogenous source finishes. So as you can see here, these are our exogenous sources. Any excess glucose that we have, we create something called glycogen, which is the storage of glucose. One good thing about glycogen is that it's very easy to break down and utilize, but a small issue is that it is quite bulky, so it is very hard for us to store it in big amounts. So the amount of glycogen would last us around 2 days at most. And then we have our star of today's show, which is basically gluconeogenesis, which is basically we make new glucose from other sources. The process starts slowly from the 8th hour, and it can last us during our fasting state. So why is this important? Well, of course, we need energy, and we need continuous amounts of glucose. Especially there are some organs that really depend on glucose, such as the brain. The primary source of energy is through glucose. Unless we go through extreme starvation, then we rely on other sources such as ketone bodies. On the other hand, basically red blood cells sacrificed everything to carry our hemoglobin. So they don't have mitochondria, so they cannot really produce the other sources of glucose. So they rely exclusively on glucose as a source of energy. And of course, we have the cornea, lens, kidney, but these organs are the primary focus that we focused here on the lecture. So let's talk about what is gluconeogenesis. So let's break it into three parts. We have gluco here, which is basically glucose, neo, so making new glucose from sources that are other than carbohydrates. So basically it is an energy consuming. So I mean, we pay to make new glucose. Anabolic, we build something. So we take a random precursor and we make it to a glucose molecule, and we utilize non-carbohydrate precursors. You may ask, what are non-carbohydrate precursors? Examples are glucogenic amino acids, basically most of the amino acids, except leucine and lysine. We have pyruvate, which is the end product of glycolysis, lactate, which is the end product of anaerobic glycolysis, and we have glycerol, which is basically fat. So when we need to break down fat, that's when we create glucose via gluconeogenesis. Of course, we have also odd-chain fatty acids, which is basically propanoic acid. Just to know that gluconeogenesis happens primarily or mostly in the kidney and the liver. It can happen in the kidney, but it's mostly in the liver due to other parts of the body not having an enzyme, which we will touch upon, inshallah, later. So when do we need gluconeogenesis? So basically, when do we need to create more glucose? Can someone answer? Okay, I'll continue. So we do it basically when we don't have energy. So we don't have abundance of glucose. We need it to function, and the levels are quite low. So basically, when we eat, we have high insulin, so we have a hyperglycemic state. So we have a lot of glucose. So if we fast, we do not have as much glucose. So we need to push and activate gluconeogenesis so we can replenish these stores. So just a small recap. These are a few questions. So we said gluconeogenesis makes glucose from non-carbohydrate precursors. Glucogenesis happens in both the liver and kidneys, but it mainly happens in the liver. So to understand gluconeogenesis, we need to understand glycolysis, which is basically the breaking down of glucose into our energy currency, which is basically ATP. So we start, as I said, I've had my shawarma. It got into my muscles through a transporter, and now I have glucose. So to trap it, we phosphorylate it. So we have glucose 6-phosphate, and then we go throughout the cycle and so on till we end up with pyruvate. And then the Krebs or TSAA cycle starts, where we go through this cycle again and again. I won't bore you with the details, but we need to know one very important thing. That in glycolysis, there are 10 steps. 7 of them are reversible. 3 are not. So step 1, step 3, and step 10 are the most important, since they are very hard to reverse, since they require a lot of energy to be made. So to phosphorylate the glucose at first, to add another phosphate to glucose 6-phosphate to make it fructose 6-phosphate to make it fructose 1,6 bisphosphate, and to change this long word, which is basically going to call it PEP, to pyruvate. So as you may see here, glycolysis and gluconeogenesis are basically the inverse of each other. But it is not as simple as that. As I mentioned before, we have our 3 very big steps. Those are the irreversible steps. But again, we really want to go back to glycolysis. The question is, can we go through it directly? No, these steps are irreversible. So we need to bypass them in gluconeogenesis, and I'll inshallah be diving into each step. So these are the 3 main enzymes in glycolysis. So we have pyruvate kinase, which phosphorylates glucose, PFK1, which is basically the rate limiting step of glycolysis. Glucokinase is where you phosphorylate, and then we have PFK1, and then pyruvate kinase is the last step. Then we have these enzymes, which we're going to talk about in details in gluconeogenesis. So let's start step 1. So we start all the way from the down here. We have pyruvate. We want to go back, but the thing is, this reaction requires so much energy that we cannot go back directly. So what do? We try to escape it. How do we do that? So basically, glycolysis happens in the cytosol. But in order for us to make PEP again, we need this compound, which is called oxaloacetate. And as you remember, oxaloacetate is a component in the Krebs cycle. So what do? We go to the mitochondria, for this all happens in the liver, and we try to create oxaloacetate. So basically, our pyruvate goes and becomes acetyl-CoA and goes through the cycle here. And then it does not go to oxaloacetate in the mitochondria. It does something called a malate shuttle, which basically it stops at malate. Malate can escape from the mitochondria and goes to the cytosol. And then it can be turned into oxaloacetate using the enzyme called pyruvate carboxylase. So this enzyme is very important, as it needs 3 things. Any carboxylase enzyme needs 3 things: ATP, CO2, and biotin, which is vitamin B7. So after that, we have our oxaloacetate. We want to turn it into PEP, which is the compound we couldn't reverse here, which is basically what we need. We use something called phosphoenol pyruvate carboxykinase, basically PEP-CK. So we use a 2-step process. We go from pyruvate to oxaloacetate through the malate shuttle, using the enzyme called pyruvate carboxylase, and then the oxaloacetate to be turned into PEP. We need the PEP-CK enzyme. One important thing we should mention here is that this enzyme can be stimulated with acetyl-CoA, which is basically when we try to enter the cell, our body basically notifies us, okay, we're trying to escape, so it helps us activate the enzyme to turn malate and to turn malate pyruvate or to oxaloacetate. So, and then the way is very easy afterwards. You can go back, go back, go back, go back, go back till we reach this step. Again, fructose 1,6 bisphosphate is a very energy dependent reaction. And it's very important since PFK here is the limiting step in glycolysis. And the limiting step of gluconeogenesis also happens to be fructose 1,6 bisphosphatase. So again, this is the component we have. So in normal glycolysis, when you try to break down glucose, we take fructose 6 phosphate, we add one more phosphate group using PFK. So it's a kinase. It adds a phosphate. So we have our high energy molecule, which is basically fructose 1,6 bisphosphate. And in gluconeogenesis, we basically want to do the reverse. So what do? We try to remove the phosphate from this component. So we use an enzyme called a phosphatase. So this step is basically called so this enzyme is basically fructose 1,6 bisphosphatase. So a phosphatase basically means we remove the phosphate. This step is very important. As I said, it is the rate limiting step, the most important step in this reaction. So if you remember from glycolysis, this I'm going to touch upon this twice to make sure this concept is very clear. Going from fructose 6 phosphate to fructose 1,6 bisphosphate requires another component, which is basically fructose 2,6 bisphosphate. So if we have fructose 2,6 bisphosphate, that means we want to push it through the glycolysis way. So if this is a stimulator to glycolysis. So if we have this component, that means we go down. We try to break down glucose, not make glucose. So if we have low amounts of this component, just fructose 2,6 bisphosphate, that means we want to go up. So we want to make gluconeogenesis. So having this enzyme at low levels, which means basically that we want to have gluconeogenesis. I hope this point's clear. I'm going to repeat it again, inshallah, in a more clear area. So going to step 3, which is last but not least, we want to remove the last phosphate group so we can have our goal product, which is glucose. So we take glucose 6 phosphatase. So a phosphatase removes a phosphate, and then we end up with our glucose. Ta-da! That's basically gluconeogenesis. We started from pyruvate, went back all the way, went through our 3 steps, and then ended up with a product that we wanted, which is basically glucose. Is this the end? Nope. So let's try and recap. What was the rate limiting step in gluconeogenesis? Can someone answer? Is there? Come on, it's an easy question. I don't think if someone's writing the chat, I don't think I can see it. Oh, no worries. I'll continue. So basically, the rate limiting step is fructose 1,6 bisphosphatase. Remember that we tried to remove the phosphate from the fructose 1 bisphosphate using the phosphatase enzyme. This is the easiest way to understand. So, and then we have this question, which basically says there are the X amount of reversible steps through perfect 7. Yes, thank you so much. So we have 7 reversible, 3 irreversible. Okay, so now we touch upon how do we regulate the cycle. So we don't just have random glycolysis and gluconeogenesis happen. We basically cannot have 2 cycles that are doing the opposite. So we cannot build and destroy at the same time. So basically, let's take another look at it. We have glycolysis. It happens in the cytosol. We have gluconeogenesis. It happens in the cytosol and the mitochondria. We know our rate limiting steps and we know when it happens. So what stimulates glycolysis? Basically, we have a lot of glucose. We want to burn. So when we have a lot of glucose in our blood system, we basically produce insulin. And if we have AMP, which is basically a sign of low energy, want to create more energy, we also go through glycolysis to replenish our ATP. And as I mentioned before, we have fructose 2,6-bisphosphate. For our gluconeogenesis, it's the other way around. We do not have the access and abundance of glucose. So our body produces glucagon, and glucagon is the main stimulator for gluconeogenesis. For inhibition, it's the other way around. So let's go back here. As we said, glucagon is the main regulator of gluconeogenesis. Again, remember that we are in a fasting state. In gluconeogenesis, we're trying to make glucose from other sources. We are done with our food. There is no food ahead of me. I need to burn from my storage. So what does insulin or glucagon do? So a rule of thumb, whatever stimulates glycolysis inhibits gluconeogenesis. So if we have high levels of fructose 2,6-bisphosphate and we have elevated levels of AMP, does that elevate gluconeogenesis or inhibit it? Let's see if anyone answers. So it basically inhibits it. Those factors are activators for glycolysis. They are inhibitors of gluconeogenesis. For ATP and acetyl-CoA, those can be activators for gluconeogenesis, meaning they are repressors of glycolysis. So there are other sources that activate gluconeogenesis. So we have cortisol and thyroid. These you'll take inshallah in Endorepro, I think next semester. And for epinephrine, it is basically, when do we produce epinephrine? Is that when we try to run away, fight or flight reaction. So we need the highest amount of energy in our blood to run away. So that's why we have gluconeogenesis, we have glycogen breakdown, and so on. Okay, this is, again, I'll mention it again. The very important point is that the PFK1 in glycolysis, which is basically the rate limiting step, is affected by our component, which is fructose 2,6-bisphosphate. So if you have elevated fructose 2,6-bisphosphate, that helps us go through glycolysis. So it helps us produce more energy. When is that seen? In insulin. So in high levels of insulin, meaning we are in a very fed state. So why is all of this important for us as future clinicians, inshallah? So a very famous drug, I think Dr. Jada talked about it endlessly in your lectures, which is basically metformin. So metformin is an infamous type 2 diabetes drug. It inhibits gluconeogenesis. So it does that through a lot of ways. You don't need to know them, but what you need to know is why do we do that? So basically, in our fasting state, we try to elevate our glucose levels. As a diabetic, you're trying to avoid elevating your glucose levels as much as you can. So basically, this drug inhibits gluconeogenesis. Another important clinical fact is biotin deficiency. So we needed biotin in the first reaction or first step of gluconeogenesis, which is basically turning the pyruvate to oxaloacetate through the enzyme pyruvate carboxylase. And biotin, the fun fact about it is that when you consume a lot of raw eggs, there's this component called avidin, which just basically binds to biotin and makes it not available. So basically, don't consume a lot of raw egg whites. Sorry. Last checkpoint, inshallah. So basically, gluconeogenesis is inhibited by insulin. That's right. Gluconeogenesis happens in cytosol only, or in cytosol and mitochondria. Both. That is true. Thank you, Ahmed. So okay, we have our cycle. We remember you said the two steps here through PK and then PepCK. Our rate limiting step, which is fructose 1,6-bisphosphatase and glucose 6-phosphatase. So it's not always pyruvate that we're looking for to build energy. So we have other sources. So we have two other cycles that are very important for us to understand. They're very simple, not too difficult concepts, but again, If you remember, we said gluconeogenesis, breakdown, creation of glucose from other sources. So not all sources have pyruvate as their precursor. So let's explain first the alanine glucose cycle. So basically, it's a very simple cycle. You start here. This is the muscle. We have glucose. So let's say this is me. I am going on a run. At the start, I'll finish most of my glucose. I'll turn it to pyruvate. And then there is no time. There is high demand. I'll start going through anaerobic glycolysis. So no oxygen. So we produce lactate. These byproducts can be turned from pyruvate to alanine by an amino acid that donates its amine group and turns it into alanine. Why? We'll see now. So the alanine leaves the muscle, goes to the liver. As soon as it goes to the liver, it can donate the extra amine group that was given, and this goes through the urea cycle. I'm not sure if you take it this semester or next semester, but the urea cycle is a very interesting topic. And then it goes through, it comes back to pyruvate and it goes through gluconeogenesis, and then we have glucose again. So the glucose can go back. This is very important for us to replenish the glucose sources from the muscle to the liver. And again, remember, why can't we have gluconeogenesis in the muscles? Because the muscles lack the enzyme glucose 6 phosphatase, which is the last step of glycolysis. The other cycle we have is the lactate cycle or the Cori cycle. Basically, again, we go through the muscle. I'm working out. I have my pyruvate. If pyruvate goes through anaerobic glycolysis due to high demand, it turns to lactate. The lactate itself can leave the cell, go to the liver, come back as pyruvate, and then this pyruvate can go through gluconeogenesis again, which can lead back to the muscle with new glucose. So again, all the ways bring us to all the roads lead to Rome. So basically, a lot of end products, a lot of substrates, but our main product is to have glucose. So I'll conclude with asking a few questions. These questions I found pretty interesting. So let's see if we can go through them and you can help me with them. So question 1. Acetyl-CoA enhances the rate of gluconeogenesis by acting as an obligate activator to which of the following enzyme? Phosphoglycerate kinase, phosphoglycerate mutase, pyruvate kinase, or pyruvate carboxylase. Let me see the chat. Does anyone know the answer? Okay. Yes, perfect. The answer is D. So basically, acetyl-CoA, as you remember, is the next step we took for us to escape the first step. So we went down to try to escape, and we went through we tried to create oxaloacetate. So the first step was using pyruvate to convert to oxaloacetate using pyruvate carboxylase, which is activated by acetyl-CoA. So next question. Question 2. Which of the following compounds would be utilized? Let me say it another way. I'm going on a diet that has no carbohydrates. What products would I be mainly using to create glucose as an energy source? So acetoacetate, cholesterol, or glycerol. So let me go back to the slide to show you. So other substrates we can use through if you're not taking carbohydrates is glucogenic amino acids, pyruvate, lactate, and glycerol. Glycerol is basically our fat. So if I'm not having carbohydrates, my body will tend to go utilize fat as its main energy source. So I hope this question is clear. Let's go to my final question. So, true or false? The purpose of the Cori cycle, which is basically the lactate cycle, is to shift the metabolic burden from the muscles to the liver. True or false? This is the easiest question I've had. So again, I'll be working out. I produce a lot of, I'm going through anaerobic glycolysis. I have lactate. I don't know what to do with it. So I put it to the liver. So yes, it is true. We use that to shift the burden, the metabolic burden from the muscle to the liver, and then we go through gluconeogenesis, and then we have a new glucose. So by that, I conclude my session. I hope it was easy and simple. If you have any questions right now, please feel free to ask me. If you're watching the recording, all the best. I know you may be cramming for your exam or you're studying lecture by lecture, which I commend, mashallah. If you have any questions about the topic or any other topics, please don't hesitate to reach out. I'll be happy to help. Thank you and have a nice evening. And yeah, again, please don't forget.